In this video, I will show you how to find points of inflection. Now, a point of inflection is where the graph changes from being concave up to concave down, or from concave down to concave up. This cannot be an asymptote or even a sharp turn like you would find in a piecewise function. But for example, so here is a function that is concave down, and then imagine right around here it switches to concave up. So this point right here would be the point of inflection. We have learned that a function will be concave down in intervals where the second derivative is negative. So where the second derivative is less than 0, it'll be concave down, and where the second derivative is positive, that's where it will be concave up. So keep that in mind as we look at example 1. Find the points of inflection. Find the open intervals on which the graph of f of x is concave up or concave down. So we are going to use the second derivative test to determine where the function is concave up and concave down. And in the transitions between the two, that's where the points of inflection should be, as long as there are no asymptotes. We can see in this problem there's no denominator, so there won't be any asymptotes to worry about. So it's all about the second derivative test, which means that first we need to do the first derivative. So the first derivative, using the power rule, the 4 goes in the front, reduced by 1. In the next term, the 3 goes into the front and makes 12. And reduced by 1. So there is the first derivative right there. Now let's go ahead and do the second derivative. So power rule again, 3 times 4 is 12, reduced by 1. 2 times 12 is 24, and reduced by 1. So this is the second derivative. Okay, we need the critical numbers where the second derivative is equal to 0. And normally we would also ask ourselves where the second derivative is undefined. But there are none of these. There are no denominators here or anything like that. So we don't have to worry about that second one. So just focus on where the second derivative is equal to 0. So setting this equal to 0, we see that both terms have a 12, so there's nothing to stop us from dividing both sides by 12. Just to make our job simpler. So that's going to leave us with x squared minus 2x is equal to 0. Now let's take out the GCF of x. So that will leave us with x minus 2. So using the zero product property, either x equals 0 itself because of this guy, or x minus 2 equals 0, which means that x would equal positive 2. So these are the two critical numbers where the second derivative is equal to 0. So these are possible locations of a point of inflection, but we won't really know until we do the second derivative test, which means that we need to set up a number line, and we will create intervals using these values. So let's go ahead and put the 0 right here, and we'll put the 2 over here. I'm going to label this side of the line as f double prime to remind us that whatever calculations we do will be second derivative evaluations. We're going to need some test values. So for example, in this interval, I think I will use -1. And in this interval, I will use positive 1. You know what? I like to change colors when I do this. So in this interval, I will use positive 1. And in this interval, I will use 3. Okay, so let's evaluate the second derivative. So we've got 12x squared minus 24x. Okay, so that's going to be 12 times negative 1 squared minus 24 times negative 1. Negative 1 squared is positive 1, so this will just be 12. And negative times negative is a positive. So what matters is that in this interval we are getting a positive number. That tells us that the function itself will be concave upwards in this interval. All right, now looking at the middle interval, evaluating the second derivative at 1 will give us 12 times 1 squared minus 24 times 1. So this will just be 12 minus 24, which is going to be a negative number, which tells us that the original function will be concave downward in this interval. Let's check the final interval at 3. All right, second derivative, of course. So this will be 12 times 3 squared minus 24 times 3. Okay, so this is going to be 12 times 9. So that's going to be 108. And minus 24 times 3, so that's minus 72. So this is going to be a positive value. That tells us that in this interval, the function will be concave upward. All right, so it's time to answer the question. So since the function is transitioning from concave up to concave down at 0, that tells us that we will have a point of inflection right here. So let me go ahead and label this up. I'm going to say points of inflection. All right, so we know we're going to have a point of inflection at 0 comma something. Let's go ahead and find the y value while we are at it. So for the y value, we need to go back to the original function. Okay, so if we substitute 0 for x, both terms will be 0. So the y value will be 0. So we have a point of inflection at 0 comma 0. So we have another point of inflection over here at 2 comma something, because the function goes from being concave down to concave up. So what's the y value that goes with this 2? All right, I think I can squeeze it in right here. So if I do f at 2, all right, so that would be 2 to the 4th power minus 4 times 2 to the 3rd power. So that's going to be 16 minus 4 times 8. So that's going to be 16 minus 32, which is going to be negative 16. So that's the y value. So 2 comma negative 16, whoops, is the other point of inflection. So for this problem, we were also asked to find the intervals of concave up and concave down. So we might as well answer that as well. So the function is going to be concave up from negative infinity to 0. and also from 2 to infinity. And the function will be concave down in the single interval from 0 to 2. Before we move on, let's take a quick peek at the actual graph. We said there would be a point of inflection at 0, 0, and another one at 2, -16. So that does appear to be the case. Visually, we can see that the function is concave upward in the interval from -infinity to 0, and then it turns and becomes concave downward from 0 to 2, and then it shifts again and becomes concave upward from 2 to infinity. Let's do one more example. This time we're going to find the relative extrema. In the past we have used the first derivative test to tell us where the function is increasing, because that'll be where the first derivative is positive, and where the function is decreasing, because that's where the first derivative is negative. And where the function went from increasing to decreasing would usually be a relative maximum. And of course, if it went from decreasing to increasing, then it would be a relative minimum. So that's how we used to do it. And we will still sometimes do that. But I want to point out to you that we can also use the second derivative and concavity to help us find relative extrema. So let me show you what I mean. Let's go ahead and find the first derivative just so that we can then find the second derivative. But using the power rule, 5 times -3 is -15. So we have -15 x to the 4th power, 3 times 5. We get that 15, reduce the power by 1. So here's the first derivative, and let's take the derivative of the derivative for the second derivative. So this is going to make -60 x to the 3rd power plus 30 x. So here's the second derivative. So obviously there are no places where the second derivative will be undefined. There are no denominators or square roots or anything like that. So all we have to worry about in terms of critical numbers is where the second derivative is equal to 0. So setting this equal to 0, we notice that both terms are divisible by 30. So we might as well simplify this by using that. So let's divide both sides of the equation by 30. I don't know why I did put a negative right there. Didn't really mean to do that. I'll just go ahead and leave it like this. Okay, but you know what? Now that I think about it, I don't like having a negative in the front, so maybe I will divide by -30. Okay, maybe my subconscious knew that would be better. So dividing by -30, we will have positive 2x to the 3rd power minus x is equal to 0. So there's a common factor of x, so I'm going to take that out, put it in the front. So that's going to leave 2x squared minus 1. Setting each of these equal to 0 because of the 0 product property, I'm going to get x equals 0 right away from this guy. And if I set 2x squared minus 1 equal to 0, then I'm going to end up with 2x squared equals 1, added 1 to both sides. Dividing both sides by 2, we get x squared is equal to 1/2. If I take the square root of both sides, I'm going to have x is equal to plus or minus, well, the square root of 1/2, all right, in my head, I understand that this is 1 over the square root of 2. And if I rationalize the denominator, that's going to be radical 2 over 2. So that's what I'm putting here. So plus or minus radical 2 over 2. So we have 3 critical numbers. We have 0, and we have plus or minus radical 2 over 2. As we use the second derivative test to determine concavity, keep in your mind that radical 2 over 2 is approximately 0.7. So this is about negative 0.7, and this is approximately positive 0.7. Just keep that in your mind. So test values in the first interval, we can just use -1. In the next interval, we will use -1/2. In the next interval, we will use +1/2. And in the last interval, we will use +1. And I copied the second derivative here for reference. So we're going to have -60 times -1 to the 3rd power plus 30 times -1. -1 to the 3rd power is still -1. Negative times negative is a positive, so that'll be 60. And then 30 times -1 is -30. That's going to leave us with a positive number. That tells us that the function will be concave upward in this interval. Okay, let's take a look at -1/2. All right, I'm going to need a little bit more space for this, I think. So let's see. We'll have -60 times -1/2 to the 3rd power plus 30 times -1/2. Okay, so this is going to be -1/8. So that's just going to be 60 over 8. All right, negative times negative is a positive. And this is going to be -15. And that's -7.5 minus 15. So not negative, that's 7.5 minus 15, which will be a negative number. So in this interval, the function is concave down. Going for the +1/2, and I'm really running out of space here, so maybe I'll squeeze it in above at first. So I'm going to have my -60 times +1/2 to the 3rd power plus 30 times +1/2. So 1/2 to the 3rd power is 1/8. So this will be -60 over 8 plus 15. So this will be -7.5 plus 15, which will be a positive number. So that means that the function will be concave upward in this interval. And finally, the value of +1. So if I do -60 times 1 to the 3rd power plus 30 times 1, that's just going to be -60 plus 30, which is a negative value. Whoops. So this tells us that in this final interval, the function will be concave down. Don't forget that our objective for this problem is to find the relative maxima and relative minima. So we will still need the first derivative. We're not going to use the first derivative test, but we need the critical numbers in order to find the places where the slope is 0. Because where the slope of the function is 0, that is a potential relative max or relative min. So let's look at the first derivative and find the critical numbers. So you know what? I think I can squeeze it in over here off to the side. Okay, I'm going to use this space. So again, there are no denominators or square roots or anything, so we don't have to worry about where the function is undefined. So the only critical numbers will be where the first derivative is equal to 0. So setting this equal to 0, we have negative 15x to the 4th power plus 15x squared is equal to 0. Let's divide both sides by negative 15. So I'm seeing that common factor there. And I like the leading coefficient to be positive. That's why I picked negative 15. So that's going to leave me with x to the 4th power minus x squared is equal to 0. So we have a common factor of x squared. So let's go ahead and pull that out in front. So that'll leave x squared minus 1. Using the zero product property, I'm going to set x squared equal to 0, and I'm going to set x squared minus 1 equal to 0. This will immediately give me x is equal to 0. Just take the square root of both sides. So that is one critical number. Adding 1 to both sides, I'm going to get x squared equals 1. And if I take the square root, I get x is equal to plus or minus 1. Or I could have factored using the difference of two squares. Either way, I get these three critical numbers. Notice that I'm labeling this side of the number line as f prime to show that the critical numbers that I write up here are critical numbers associated with the first derivative. So the critical numbers were negative 1, so I'm going to put a big old negative 1 right here. All right, we did have a critical number at 0, again, and we had a critical number at positive 1. So I don't need to do the first derivative test. In other words, I don't need to test each of these intervals and find out where it's negative and positive. These critical numbers tell me where the possible extrema are, the possible maxima or minima. I really can rule out 0 because the function does go from being concave up to being, it goes from being concave down to being concave up. So that means at 0, there is a point of inflection. It's doing this type of thing, concave up to concave, concave down to concave up. That's going to be a point of inflection. There's no way that's going to be a max or a min. However, at negative 1, the function is concave down. That tells us that we're going to have a relative min right here. At positive 1, the very fact that the function is concave down in that interval, that tells us that we're going to have a relative max right here. So let's go ahead and find the y values, but we're going to have a relative min at negative 1 comma something, and we're going to have a relative max at positive 1 comma something. So to find the y values, we need to consult the original function. So here's the original function. If I use negative 1, so that would give me, okay, so f at negative 1 will be negative 3 times negative 1 to the 5th power plus 5 times negative 1 to the 3rd power. So that's going to give me negative 3 times negative 1. The odd power, this stays negative 1. So this will be positive 3. This stays negative 1, so that'll be negative 5. So that's going to give us a negative 2. Okay, so we have a relative minimum at negative 1 comma negative 2. So how about positive 1? So let's just switch that out for positive 1. So that'll give us negative 3 times 1 to the 5th power plus 5 times 1 to the 3rd power, which of course will just be negative 3 plus 5, which is positive 2. Okay, so we have a relative max at 1 comma 2. And don't forget that we had a point of inflection right here. Point of inflection. And this is going to be at 0 comma 0 because we can easily see if we put in 0 for both of these, we would get 0. So before we end the video, as I love to do, let's take a quick peek at the actual graph and see how it compares to all of the predictions that we just made. So we can see that as predicted, we have a relative min right here at negative 1 comma negative 2. And we have the relative max that we found right here at 1 comma 2. Also notice the point of inflection that we found at 0 comma 0. And I'll just put POI for point of inflection because we knew that the point of inflection is where the function goes from being concave down to being concave up. So there's no way that could have been a max or a min.